Hello and welcome to my apparently much anticipated Paper 2 OCR A-Level Revision Guide. Thank you very much for all your kind words and comments that you've posted. I really do appreciate it. This is what we're going to be studying today. This is the advanced information released by the OCR exam board. Based on our understanding of Paper 1, the advanced information counted for about 75% of the total grade. So unfortunately, you will have to revise the entire content for Paper 2 to make sure you can get 100% of the grade. But if this is similar to Paper 1, the bulk of your revision should be from the advanced information that's here. This should count for most of the marks that you're going to get. We're going to start with thinking abstractly. Abstraction is a representation of reality. It requires recognizing what is important in a problem, then devising a means effectively to code it, to write it down and formulate it in a way that can be passed to an algorithm. In computer science, abstractions are used extensively. For example, variables, objects, data structures. We can also use abstraction to help solve problems without using computers. Got to be careful with that because sometimes they'll give you an abstraction question that's not necessarily related to computer science, but you have to apply the same techniques. Abstraction helps us maximize our chances of solving a problem by letting us separate out the component parts and deciding which are worth investigating. It may make a problem easier to understand, a system quicker and easier to use, or a problem easier to solve or program. Subroutines and libraries are good examples of abstraction, which leave our main program easier to understand and quicker to debug. Abstraction allows us to concentrate on what is important, or just one thing at a time. In a complex system, it is often useful to construct an abstraction to represent a large problem, and to create lower-level abstractions to deal with component parts. The power of this approach is that the details in each layer of abstraction can be hidden from others. This frees up the solution process to concentrate on just one issue at a time. Moving on, let's think about thinking ahead. Thinking ahead involves planning inputs and outputs. It is useful to apply this approach to other problems by asking, what answers do we need? What do we need to know or have before we can get what we need? Two key aspects that we need to think about are caching and reusable components. Caching, this is when data that has been used is stored temporarily in case it is needed again. This could be stored in cache or in RAM. Don't get mixed up here. When we talk about caching, we're not specifically talking about cache memory. Cache memory is just an application of this concept. If you're running data a lot in a program, as a programmer, you might make the decision to store that in RAM rather than having it on secondary storage all the time. This allows for faster use in the future than fetching it from secondary storage or even from online usage. Reusable components. This is one piece of code that can be used in multiple places or called many times. Examples of reusable components that you should be familiar with are the use of subprograms, the use of classes, and the use of external libraries. Let's take a look at some coding theory. We'll start with something a little bit complicated. Let's look at recursion. Recursion is where a procedure or a function calls itself. It is another way of producing iteration. Be careful though, recursion will call a Stack Overflow error if a terminating condition is not built in. Have a look at these two examples. These are an iterative and recursive solution to count how many times the number is exactly divisible by 2. This is in exam pseudocode, but I'm sure you could convert this to the programming language of your choice. First of all, let's look at the function iteration. This should be fairly familiar with you. We've got the while loop there, so we know it's iteration. It's just going to repeatedly divide the number by 2, check to make sure it can divide it evenly by 2 by using mod, add 1 each time, and return that final value. The recursive function is a little bit more interesting. Does the same job, but might look a little bit more complicated if you see it in the exam. So how does that work? Well, you'll notice there is no loop. There's no for loop or while loop. We start with count equal to 0, and then we have our condition. If the number is greater than 0, and the number can be exactly divisible by 2 in that it has no remainder, we add 1 to the count, we divide the number by 2, and then we say count equals count plus we call the recursion function again, passing it the value of number. So until that if condition is falsified, it will keep calling recursion over and over and over again, counting up how many times things can be divided by 0. Eventually that condition will become false, hopefully if you programmed it correctly, otherwise you'll get Stack Overflow when you run out of memory. But eventually it will become false, it won't execute the if condition, and instead it will go to return the count value. And this will kind of unwind the program. It'll go back through all the recursions until it gets to the original function and returns control to where it was called from. Let's take a quick look at variables, local and global. Global variables can be accessed throughout a program. They are declared or set outside any function, procedure, subprogram, subroutine. Local variables are declared inside a function or some other type of subprogram. They can only be accessed from within that subprogram. Global variables can be dangerous. It is easy to overlook them when they are changed. For that reason, we tend not to use global variables if we can help it. We prefer to use local variables. Moving on, let's take a look at modularity. So most programs are written in separate subsections. This makes it easier to create and test them. These subprograms can have various names depending on the programming language that you're using. Sometimes they're called subprograms, subroutines, functions, procedures, etc. Typically in the exam we're looking at functions and procedures. Functions are subprograms that usually return a value, whereas procedures perform some kind of operation but do not return a value. Sometimes subprograms need some data to carry out their instructions. This is done by adding some variables, typically in brackets, after the subprogram name. These variables are called the parameters. Corresponding to each parameter in the subprogram definition is an argument in the subprogram call. So you can see here we've got a simple procedure called greeting. After the procedure heading, we have in brackets name. Name is a parameter, that is some data that will be sent to the procedure that it can use. And underneath that, we've got the main program. And here we call the procedure greeting, and we're going to give it an argument, name. So we send an argument, but our subprogram receives a parameter. Parameters can be passed in one of two different manners: by value and by reference. By value, this is the default in many programming languages and the default in your exam. So if you don't say anything or you don't read anything, you can just assume that it's by value. Here, when you pass a parameter, a copy is made for the subprogram. So changing the value in the subprogram does not change the original value. By reference, on the other hand, this means the address of the variable is passed to the subprogram. In this case, if the variable is changed inside the subprogram, it stays changed throughout the program. So in the first example here, we've got our procedure add, and you can see we are passing the parameter num by value. So in our main program, we set the value num to 10. We call the procedure add, passing it that value, that 10. So 10 is sent, the value 10 is sent. It's received by the procedure. We create a kind of local variable called num. We add 10 to it, and then we print it displaying 20. The procedure ends, goes back to the main method there, where we print the value of num, and we still get the value 10. So in the main program, num has the value 10, even though we added 10 to it in the procedure. This, however, does not affect anything outside of the procedure. The value num does not change outside of this. In the other example, however, we are passing it by reference. So that means we are passing a pointer to the same memory location. So if we change the value now, it will change the original. So in our procedure, again, we add 10 to it, we print it to display 20, we return control back to the original program, and we print out the value again, but this time instead of displaying 10, it displays 20 because we've passed the value by reference. When we changed it, it changed the value throughout the program. Moving on, let's take a look at IDEs, Integrated Development Environment. An IDE is a comprehensive set of tools to develop programs. Common features that you will find in many IDEs include an editor, often optimized for one or more languages, error diagnostics such as tools for debugging, step-by-step progression through a program, a build feature that compiles and links with other parts of the program, version control, a runtime environment to allow the programmer to run the code and see the output from the IDE itself, and a translator such as a compiler and possibly an interpreter. Now let's take a look at object-oriented programming, or OOP. I'm not going to go too much into the theory of OOP, but please research that yourself as part of your studies. I'm just going to look at the coding. So again, looking at the coding from the point of view of the exam language, the exam pseudocode. First of all, let's look at creating a class and a constructor. So we do that by saying class and then the name that we've decided for our class. Make sure you read any exam questions carefully to use the name that they're expecting. After that, we declare all of the attributes that we need for that. In this case, we have one example. We say private name. Typically, attributes will be private unless you're told otherwise. Then we have the constructor. The constructor has to be public because it has to be called from other programs. And we say public procedure new. New is the key word here. New lets the examiner know that this is the constructor that you're using. And then we have a list of any parameters that were being sent, in this case given name. And then inside the constructor, we just set all the attributes to either default values or values that were passed to it as parameters. To instantiate a new object from another class, we do it like this. It's the generic name of that class, then the name that we've decided for this particular instantiation, equals new, and then the name of the class, and then any parameters that we want to pass to the constructor. This line of code is really important. I've seen exam questions in previous papers where this one line of code was worth 4 marks. So make sure you do know how to instantiate a new object, because simple one line of code could be worth quite a few marks. To create methods for our pet class or any class, we are going to use either procedures or functions depending on if we need to return a value or not. Typically, these will be public unless you're told otherwise. If they're private, they can only be called from inside that class. They can't be called from outside. So typically, they're going to be public. Again, very easy. Public, and then either procedure or function. Give it the relevant name, and then pass it any parameters required, if any, and then do the coding that you need inside. Remember, if it's a function, it will return a value. Then, to call these methods from another class, it's the name of your instantiation of that object, in this case my pet, dot the name of the method, and then in brackets any parameters that you need to pass to it. So in this example, myPet.setName Spike. Print myPet.getName. Looking at some of the more advanced features of OOP, inheritance and polymorphism. Inheritance allows a class to inherit all methods and attributes of a parent class, as well as having its own. So here we've got class dog. We know it inherits from the pet class because it uses the keyword inherits. Make sure you use that. That'll be worth a mark right there. By using this inherits keyword, we can automatically have all the attributes and methods from the parent class, but we can add our own special attributes and methods as we need them. So here we've got private breed, which is only for the dog class. It's not going to be in pet. However, all the original pet data is still included. We then have our constructor using public procedure new. Inside our constructor, we're using the super keyword, super.new given name, and super will call the original constructor, the parent constructor. In this case, the original pet constructor will be called using the value given name, and then we can set the breed value because that's an extra part of our dog class that isn't in pet. Polymorphism. This is the ability to use the same code to process different objects according to their type. Sounds very complicated, but actually it's probably not going to be too complicated to do in an exam. Let's have a look at a simple example. I'm creating a pet object called myPet and a dog object called myDog. Then I'm setting up an array for my pets, and I'm setting the first value to myPet and the second value of my array to myDog. Then I'm going to iterate through the pets array using a simple for loop. And inside that I just say pets_i.speak. Thanks to polymorphism, the computer knows which speak method to call. Does it call the pet speak method, the dog speak method? It just automatically chooses the right one. That's all polymorphism means. Okay, it sounds a little bit complicated, but it just means I can put any sort of pet objects, anything that inherits from pet, in the same array, and then when I call the method, it will use the myPet method or the myDog method or myCat method or whatever would be appropriate. Okay, that's all polymorphism means. Now let's take a look at computational methods. Backtracking. Some problems are best solved by trying out a sequence of actions and determining how far they succeed until it becomes apparent that it can go no further. Backtracking is essentially trial and error. Data mining. This examines large sets of data looking for patterns and relationships. Databases are designed to store and process data in predefined ways. When they get large enough, unexpected relationships may be uncovered, especially if other databases are examined as part of the same process. Performance modeling. Real-life objects and systems, as well as computer software, can be modeled in order to predict how they will behave when in use. Performance can depend on complexity. This can be assessed by analyzing program functions and using the big O notation to show how algorithms behave with increasing size of input. Pipelining. A common computing technique where the output of one process can be fed into another. Complex jobs can also be divided up into separate pipelines so that parallel processing can occur. This technique parallels real-life situations such as assembly line processing. Finally, visualization. Problems and data can often be better understood when translated into a visual model. Computers have facilitated many new and inventive ways to visualize situations. Often these show unexpected and interesting trends that could not be produced by traditional manual methods. The next section we're going to look at is 2.3.1 algorithms, starting with stacks. So for these algorithms, I'm not going to go into the theory in a lot of detail. You can study that yourself. I am just going to go quickly through the algorithms and maybe give you some points that you might want to think about. So when we get a stack question, please read the question carefully. The stack pointer might be pointing at the top item, as in the example that we can see here, or the next free space, and that will change how you would write the algorithm. So sometimes we want to increment the pointer first and then push the item, or push the item and then increment it. Okay, so in this case, yes, it is pointing at the top item. So we can say if top equals maximum, then print full. It's full up, stop the program. Else, increment the pointer by 1, and then we can say the top data is the item. To pop, we say if the top is the minimum, then we can print empty and stop the program. Else item equals the data top, decrement the top by 1, and then obviously we end the end if there. Now let's take a look at circular queues and push. With a circular queue, there are two possibilities for it being full. If the start pointer is equal to 0 and the end pointer is maximum, then it's full and we need to report that to the user. But it could also be full if the start pointer equals the end pointer plus 1. So again, we need to report back to the user and stop. Otherwise, if the start pointer equals -1, then we know it's an empty queue and we can set the start pointer to 0. If the end pointer is at the maximum and we want it to wrap around because we are pushing, we set the end pointer to -1, and this will implement the wraparound. At the end, we can say that the data at end pointer +1 is the data we want. Then we increment the end pointer by 1 because we are pushing and adding something to the end of the queue. Now we're popping, so we have to check that the queue is not empty. So if my start pointer is -1, then the queue is empty. So report that to the user and stop. Otherwise, pop the data off the queue. Whatever is at the queue at the start pointer becomes the data. Then I can say that if my start pointer equals my end pointer, then the queue is empty, so I can set both pointers to -1. Otherwise, if my start pointer is at the maximum, then I set my start pointer to 0 to wrap around. Otherwise, I can add 1 to my start pointer and increment it there by 1. Next, let's take a look at adding two linked lists. There are two lists, the data and the free space. That means there are two pointers to the head of the data and the head of the free space. Take a look at that diagram at the bottom. We're adding something to our list. So as you can see, E no longer needs to point to A, it needs to point to our new item, and our new item needs to point to A. This new cell has come from free space, so those pointers would need changing as well. This time we're removing something from a linked list to bypass it. So in the diagram, E no longer points to A, it needs to point to P. Remember, the current cell A needs to go back into free space, so those pointers would need changing as well. Continuing with linked lists, we have two main algorithms for traversing a linked list. We've got outputting a linked list in order, and we've got searching for an item in a linked list. Starting with the top one, set the pointer to the start value, and then loop until the pointer equals 0 or null or whatever is being used. So we go to the node at the pointer value, we output the data at the node, and then we set the pointer to the value of the next item pointer at the node. And again, we continue that until pointer equals 0 or similar. To search for an item in a linked list, again, set the pointer to the start value, repeat until the pointer equals 0 or whatever. Go to the node at the pointer value. If data at the node is the search item, we can output and stop. Otherwise, set the pointer to the value of the next item pointer at the node, and then just keep going until we reach the end. Binary trees. Remember, binary trees can be sorted or unsorted. So when you look at a binary tree, you need to check that everything going to the left is less than and everything going to the right is greater than. If we have a look at the first example here, we start with Can as the parent node. William arrives and is greater than Can, so this goes to the right. Jones is less than Can, so goes to the left. Then we have Lee arriving, which is greater than Can, but less than Williams, so we go left. Then Roberts comes along. Roberts is greater than Can, less than Williams, but greater than Lee, so that goes to the right. This also works with numbers. So if you have a look here at the other binary tree, you can see the order is 4, then 2, then 5, then 1, then 3, and that gives us a similar pattern if we go right and left at the right time. Next, we have depth-first tree traversal. In the spec, you just need to know post-order. If it's post-order traversal, we're going to go left, right, and then visit the node. In this example, we start with F. Go left, and we get our A out. Then we backtrack to B, then we're going right, and then left to get C. Backtrack to D, go right, and get E. Then, since I've been left and right, I go back to the node and get D. Then I backtrack again. I've been left and right, so I have B. Then I backtrack to F. I finished the left-hand side. Now I need to go to the right-hand side. I go right. There is no left, so I go right again. Then I go left and I get H. I backtrack. There is no right, so I have I. Then I backtrack again and get G. And then I backtrack one more time to get F. With breadth-first tree traversal, we just handle each layer. This is quite nice and simple. So we have our F, BG, ADI, CEH. There are 4 layers. Remember that with depth-first traversal, we're using a stack, whereas for breadth-first, we would be using a queue. Okay, I think I'll draw all this to a close now. I think that is pretty much everything from the advanced information covered. I hope some of that was useful for you, just a little bit of revision there, just to help prep you before you do the exam. Good luck with everything, and I'll see you in a future video.